Okay, so welcome everyone to this new Graviticulous seminar session. Sorry for the 6-minute late, but I had a audio problem, so sorry about that. So today we have Yoxara as our speaker. She obtained her bachelor degree in physics at Universidad de los Andes in Venezuela in 2016, engaging in projects related to solid physics. She also received his master's degree in physics at the Federal University of Rio Grande do Norte in 2018-2019, in which she studied beyond the standard model phenomenology. She's currently pursuing a PhD degree in physics at the Federal University of Rio Grande do Norte, and she has been a visiting student since 2018 at the International Institute of Physics in Brazil. And her research projects are theory and phenomenology of the models beyond the standard model. So Yoxara, thank you again for giving this seminar, and please go ahead.
Okay, thank you so much for the presentation. Okay, my name is Yoxara. Today I will talk about Kaon Decay to Meson energy, implication of the NE62 result for a C-prime model. This work is based on the Stoyan archive in collaboration with Tesio Melo, Sergei Kovalenko, my advisor Farinaldo Queiroz, and Clarissa Siqueira. Tesio Melo and Clarissa Siqueira is postdoc in the International Institute of Physics. Sergei Kovalenko, you know, the professor in the Universidad Andrés Bello. And my advisor in the International Institute of Physics at the Physics Department of the Federal University, Rio Grande do Norte. The overview of this talk is divided in 5 items. First, I will introduce the Kaon decay, the decay K in Python, in P and 2 neutrinos, and present the model based in the 331 gauge symmetry, the main model here that contains the C-prime gauge boson in the standard model is the 331 quick right-handed neutrino. The same conclusion and results in our work is the same going to the 331 with the heavy neutral lepton. I introduced the variation radius of this Kaon decay mode for the K plus and KL. And finally, describe the results and conclusions in this paper. Okay, the real Kaon decay is a flavor changing neutral current process. In the standard model, the main contributions is dominated for the top quarks in a loop in lowest order, and the chart contribution. Due to the gene mechanisms are the suppression of the contribution of this decay, the standard model predicts the variation ratio of this decay and is smaller. But this decay is probed with new scalar, new gauge bosons, the heavy gauge boson, C-prime in this case, and the contribution in beyond the standard model you can find here in these diagrams, where the contribution confronted to the loops with the boson W are 2 quarks here in the lowest order contribution in a loop. The main contribution analyzed in our work corresponds to this diagram. You can see the changing flavor, the flavor changing here in the quarks in the initial state, because the Kaon decay in P are in the final state. You can see the neutrino and bark neutrino. Now the current experimental states of this decay is given for 2 experiments, and existing 2 experiments are KOTO experiment. In our work, the bound using in our work correspond of the NX62 experiment in a CERN with 3 years the data, the 2016 until 2018, and the value is of the 3.4 sigma. In our results, you analyze the 11 value plus 4 and minus 3.5, the errors. The experiment is with Meson energy because, okay, in your initial state, you can have the Kaon with the momentum, the Kaon momentum, and the final state you can find the P momentum. But there are a Meson energy, and then the Meson energy is the square mass of the that is equal to the difference of the square momentums. Okay, the other modes is the Kaon air, decay and P0 and neutrino, and the upper bound is given for this value in KOTO experiment with 3 years the data too. Okay, in our work, taking into account of 2 bounds are another theoretical bounds of 2 modes in a rare decay, in a rare Kaon decay. The 331 models are a popular station in Beyond Standard model and contain new gauge boson, are new leptons in these models, and are very important because it's playing some physics in Beyond Standard model, for instance, neutrino masses, dark matter, flavor violation, meson oscillation, and contain the rich phenomenology in collider physics too. Okay, in this picture you can find, okay, what new particles appear in the 331 with right-handed neutrino. For more information, you can find this reference of this model. Okay, this model contains the same particles, the same particles to the standard model. The 3 generations of the quarks and leptons are the mediators in the forces and the Higgs bosons too. But the group of the standard model, you know, is given for this symmetry, and the station or the 331 with right-handed neutrino is given for this group. In this way, this group experienced 2 spontaneous symmetry breaking, the first to the theta electron volt order and the second to the electroweak order. The first spontaneous vacuum expectation value here is the order to theta electron volt is B key, and the new gauge boson that appear in these models now C prime, V plus or minus, or sometimes the name is W prime, and U, and all masses are proportional to this vacuum expectation value. Also, there are new exotic quarks in the theory, and the leptonic triplet are all files, fermions and scalar fields. The representation is a triplet because the group here is U3. The leptonic triplet in the model contains the same particles to the standard model, neutrino and lepton of the 3 families. And the third component here is the right-handed neutrino. In the case for the 331 with heavy neutral lepton, the difference is that instead to the right-handed neutrino, you can find the third component, you change the third component with the heavy neutral lepton. In this case, appear this particle in the spectrum particles, and there are a representation of the right files in the singlet field here of this particle. The other particles and the representation of 2 models are the same. The same gauge boson are the same representation of the triplet, the scalar triplet and quark triplets. Here you can find the representation of the quark triplets, and the first and second component in this representation are the same particles to the standard model, but the difference here is that Di and Ui are antiparticles quarks. And the third component in a quarks correspond to the exotic quark I explained in the last slide. In the scalar sector, there are 3 scalar triplets in the 2 models. After 2 spontaneous symmetry breaking, the scalar fields acquires the background expectation value. The first in the theta electron order, and the second here, the square plus of the second background expectation value here correspond to the electroweak background expectation value. This scalar field given fermion mass, but in this model is include a scalar triplet to generate neutrino masses in the same way to the type 2 system mechanisms. In this way, the scalar triplet and the triplet phi breaking the first spontaneous symmetry breaking, and this scalar existed become to the a triplet and a doublet and a singlet scalar triplets with different background expectation value, and this interaction of these new scalar fields interact with the neutrino and giving neutrino masses. The French mass taken in our work is approximately with the active neutrino masses in 0.1 electron volts, and the right-handed neutrinos lie below 1 tera electron volts, but obtain the contribution to rate Kaon decay. I don't include here all expression to the Yoxara-Lagrangian, but you can see here the main contribution to the flavor changing neutral current that correspond to the interaction to the fermions with the new gauge boson, in this way C prime, and you can see here the charged currents for the new gauge boson, the charged boson. For instance, here you can find the interaction with the fermion with the W plus, the gauge boson in standard model. The new terms here that interact the neutrino masses with the new gauge boson are the exotic quark with the new gauge boson here, violates the leptonic number and weak spin. The gauge boson C1 and C2 are the physical gauge boson, was right from the C and C prime gauge boson mixtures, where the mixture's angle is phi. In the case with phi is 0, the C prime is the same gauge boson C2, and C1 is the boson C, or the C boson in a standard model, of boson of the standard model. Okay, the coupling constant in this Lagrangian is A1 and A2 for the left and right chiral here, but the contributions of the flavor changing confront to the left chiral because the right chiral is diagonal, and the masses of the new gauge boson, I told you, depending of this background expectation value in the first first spontaneous symmetry breaking, and depending of the standard model background expectation value and the Weinberg angle. Okay, our point here is analyze the interaction to the flavor changing in the quark with the C prime and the neutrino too, because correspond to the contributions to the variation ratio in the rare Kaon decay. Here you can see the coupling constants to the C prime, the interaction C prime nu over nu, C prime D, the bar D and D. Remember that DI is the antiparticles down and S, and here is the C prime VV. All coupling constant depending of the Weinberg angle in the electroweak group of the standard model. In the flavor basis, it's possible write the main term or the Lagrangian term that contribute to the variation ratio of the rare Kaon decay here. D prime is described for the D prime is prime and B prime transpose, and of this D prime is the correspond to the standard rotation in the flavor sector of the quartz. Okay, the epsilon D is the diagonal values that correspond to the proportional or depending of the Weinberg angle. Okay, changing the basis of this term is possible to determine the delta L is there that correspond to the coupling constant of the flavor changing neutral current. In the case the SD in the interaction with the C prime. This value is very important because in our flavor version, including this work, depending of this delta. In the same way, it's possible to determine the delta nu for the interaction to the C prime with the neutrinos. The matrix here, the unitary matrix here for the standard rotation, in our case, is choose this matrix. With these values here, for instance, at 3.1 or 3.2, the product of these elements in this matrix, with the values, we can obtain the product of this VR because the coupling constant here, or the coupling to the C prime with the changing flavors, depending of this product. In our work, there are three free parameters. In this case, sigma, because sigma is the phase in a if it's the parameter phase in a matrix, in the VL matrix. The product of these VR 3.2 and 3.1. The version radius of the red Kaon Decay modes for K plus and here to process. I say, okay, this process conserves CP and this process violates CP. The version ratio you can see here in these expressions here, this relation, and the of two version ratio depending of the imaginary part of the x. X is x correspond to the the top contributions, the lowest order top contributions in a loop, and is called short distance in physics. This parameter, depending of XL, are the sum parameters of the VCKM matrix. XL contain the standard model contributions in the lowest order, include the quantum electrodynamic and electrodynamic contributions, and contain other terms with the 331 contribution. In this case, 331 with right-handed neutrinos. And here you can see the coupling constant obtained in the last slide and the parameters of the VCKM matrix and the C prime mass. But here, the expression ratio dependent too of the real part of the XF and other factor PC. PC is correspond to the contribution of the charm and all parameters here, P and kappa plus kappa L, depending of the cavido angle lambda in this expression. We know you follow the notation of this paper here for obtaining the version rating of the 331 with right-handed neutrino. These factors, these parameters here, encoding the relevant hadronic matrix elements extracted from the subtable combination semi-leptonic rates. In the beginning, I explained that, okay, in our work, you use the bounds, the upper bound for the KOTO experiment, KOTO experiment, are the bound of the N62 experiment. But there are other bound important here because two breaching radius depending on the short distance, XF, and taking into account the isospin symmetry, there are the interdependence of the two breaching ratio, sorry, and this relation corresponds to the bound, the theoretical bound Grossman-Near. This bound is described in the green region in the plot, in the right plot. The points, the blue points here is obtained changing the three parameters in these results. The product of the BL components are C prime mass and the phase sigma is, I'm sorry, delta, and include the random parameters in the breaching radius here and obtaining these points. The main point here is that the 331 with right-handed neutrinos obeys the theoretical bound because any blue points appear in the green region. And you can find here some points allowed because this band is the allowed region in a experiment NX62 with the limit of tiny in 2028. In 2018, I'm sorry. Okay. The results here, you can see two plots, then the left and the right, that for two modes in the red Kaon Decay, for Kier and K plus versus to C prime mass. The green bound here corresponds to the KOTO experiment, the bound, the upper bound. And the color bar is different values to delta from 0 until 1.5, in our case P/2. And the product of the elementary product of the BL matrix is this value 10 to the power of -3 in two plots. And here you can put, okay, for masses, for larger masses to 400 gigaelectron volts are excluded for KOTO experiment. Here, in the case, the delta is larger than 1.4. So here is approximately 4,000 gigaelectron volts, and this bound depending on the sigma value here. For the right Kaon decay, K plus decay and P plus and the neutrino, you can see the allowed values of the allowed region for the NX62 experiment here. And you can see in approximately 3 teraelectron volts in this plot, there are different masses for the larger masses of the C prime mass in this region contribute to diffraction ratio and is described in the allowed region for the experiment. Here you can see a dip, but correspond to the interference, the destructive interference between the standard model contribution and the 331 with right-handed neutrino contributions. The other results, you can see here the space parameter for this product, the C prime mass. And here you can find the 3 different regions for the exclude region in collider physics. In the channel dominant in collider physics is the C prime decay in the leptons. For the region include here for the LHC with 13 tera electron volts is the vibration rate of 50% in the charged leptons. Okay, there are other excluded regions for high luminosity or high energy. In this case, this plot is for sigma no delta equals 0. And the blue regions here confirm to the relations of the vibration ratio because we put the bound in an experiment and the values to the sigma, delta equals 0, and describe, and the other 3 parameters describe this allowed region for the NX62 experiment. In these plots, it can impose, the larger mass up to 10 tera electron volts contribute to vibration ratio approximated for when this parameter is 10 to power of -1. The other case is incrementing these parameters, delta with p/2, for instance. The restriction here is larger than the allowed region heat. In this case, our conclusions in our work, you can see here, we explore the flavor changing neutral current in process mediated by a C prime gauge bosons. Our conclusion corresponding to the 30-watt with the RHM model, but it's the same with the 30-watt with heavy neutral lepton. We compare the vibration rates of the modes K plus and KL. We include the bounds, the theoretical bound or the theoretical in experimental bound now, NX62 and KOTO experiment. And in the last results, you put the current and project exclude region in LHC in collider physics. And we found to the last result of the NX62 experiment was able to construct a large region of the parameter space, setting lower bounds on the C prime mass that can be more stringent than those from the lepton searches at the LHC. Okay, thank you so much for your attention. For any question and comments.
Thanks, Yoxara. Very nice talk. Does someone have any question? Yes, Claudio, please go ahead.
Thank you. Thanks, Yoxara, for the talk. It was very nice. I have a question about, your Z prime has like a 3-level flavor changing neutral interaction, right?
Mm-hmm.
So, well, these decays will not be so sensitive as, for example, K bar mixing. So if you have a Z prime at 3-level in K bar mixing, you could reduce it much larger than what it is. So you should check for that bound. I don't know if you did.
Okay. Yes, I understand the following. Okay, our contribution to the variation ratio for one of these interactions.
Mhm.
Is right?
Yes.
The variation ratio contains the contribution to the 331 models and the contribution in the lowest order with top a chain in a loop and child contributions because contain the standard model contributions too. Here in our source is right. The bound of the standard model is larger to the predicts, the theoretical value predicts. In the beginning I put here this value, correct?
Okay.
A moment, okay. But I understand you told me that, okay, the contribution with the right-handed neutrino is larger to the theoretical standard model value, is right? With respect to the variation ratio.
Yeah. But
It's your question.
That's not my question. My question is on K0, K0 bar mixing. It's another process. If you have a Z prime that couples to SD at tree level, you would generate a large K0, K0 bar mixing. And this is, I mean, this is being measured and it's very small. So you should check that your coupling there of the Z is small, and probably the mass of your Z prime has to be very large. I don't remember the numbers, but if you claim that you have coupling similar to standard model values or something, the mass of the Z prime will be above 100 TeV or so. So you should check that.
Okay. Yes, in this case it's larger. And well, for instance, in this case, I only analyzing the Z prime, and in this case, only taking into account of this value here. For instance, our source, our bounds, is possible that change depending. In the case I change this parameter here too, and the delta too. But we can introduce new contributions, for instance, with the scalar fields. And okay, it's possible for other studies in analyze the other contributions to flavor changing, the flavor changing neutral current, but include scalar fields and on it anyways here in the contribution to the variation ratio. But okay, in our case, the masses, the masses taking into account here, for instance, to the neutrino masses, there are constraints because, for instance, okay, in the final state, the C prime decay in the neutrino, for masses, for the right-handed neutrino have a larger mass to the 1 tera-electron volts. In this case, is applying the contribution to the variation ratio, and it's necessary to contain these masses for the neutrinos. In this case, the right-handed neutrino contribute to the white, but don't contribute to the red Kaon decay. In our case, only analyze the contribution with the active neutrinos.
Okay, thank you, Yoxara. Is there any other question? I think not. I only have a curious question on the Na62 branching ratio calculation. They do it at 68% confidence level. Do you know any reason why it's not 90 or 95?
Repeat that, please. I'm sorry.
For the Na62 branching ratio, the measurement that you used here is calculated at 65 confidence level. Just wondering why not 90 or 95?
Okay. Okay. This bound from you told me of this branching ratio with yes.
Yeah, but
50%.
from the one from Na62, it's calculated at 68% confidence level, and I was wondering why not 90 or 95, which is the usual standard procedure.
Yes, but well, in our case, you're taking into account the duration rate with the 50% in the lepton channel.
Okay. Okay, is there any other question? No? Okay, thanks, Yoxara, again for this very nice talk, and see you then all next Thursday for the next seminar.
Okay, thank you so much. Bye-bye.
Bye-bye.